Alright guys, I'm going to go over a couple of examples dealing with Carnot engines, just so that we have a little bit of practice. These are things that we didn't quite get to in class, so I wanted to make sure that you kind of had an introduction to them. So here's the first one. Water near the surface of a tropical ocean has a temperature of 298.2 Kelvin. Whereas the water 700 meters beneath the surface has a temperature of 280.2 Kelvin. It's been proposed that the warm water be used as a hot reservoir and the cool water as a cold reservoir of a heat engine. Find the maximum possible efficiency for such an engine. Alright, so we've got the water at the surface, which we're going to treat as the hot reservoir, so that's going to be 298.2 Kelvin. And then we've got the water down beneath, so 700 meters down. We're going to treat that as our cold reservoir, and that's going to be 280.2 Kelvin. And so then we're going to treat this as a heat engine. So we're going to take the heat out of the hot. We're going to get work out. And whatever doesn't come out as work is then going to be released. And so we'll release that into the cold. Alright, so that's essentially what we have. Now the question asks for the maximum possible efficiency. Now we talked about in class that a Carnot engine is the most efficient engine that you can have. Part of that is because of the specific process of the adiabatic and isothermic processes that it goes through. Alright, but that's the best that we can get. So if we do that with our Carnot engine, okay, and we talked about in class also that we can have a maximum efficiency of that Carnot engine. Now one of the equations on the AP exam which we didn't quite get to in class is that the efficiency of a Carnot engine is equal to the hot temperature minus the cold temperature. So the difference in the two temperatures divided by the hot temperature. So the bigger the difference is, the more efficient that you're going to be. Obviously, the bigger the difference, the faster the heat transfer that's going to occur. It'll be able to be more efficient. So in this case, we can go ahead and just put those numbers in. The efficiency will be 298.2 minus 280.2 divided by 298.2. And so we should just be able to work through that now. 298.2 minus 280.2 and then divide by 298.2. And there you go. You get a 0.06, so that's 6.0% efficiency. Alright, so that's fairly straightforward. That's just so that you can have the idea of the efficiency of a Carnot engine. Pretty novel idea. Maybe they'll get it to work someday. Alright, let's go on and look at one more example, one that's a little bit different. Okay, again a Carnot type engine, so this time it's telling us it's Carnot, is designed to operate between 480 and 300 K. So let's go ahead and draw our engine. We're starting at 480 K, and this is our hot, and then we've got 300 K down here, and that's going to be our cold. Now the engine actually produces 1.2 kilojoules of mechanical energy per kilocalorie of heat absorbed. So compare the actual efficiency with the theoretical maximum efficiency. Alright, so we're going to have so much heat going in. You're going to have a certain amount of work coming out, and then it's going to emit some other amount of heat. Okay? Now, the first thing that maybe we want to do is look at the efficiency. We can go ahead and get the actual efficiency of the Carnot engine just by looking at the temperatures. Alright, so let's take the efficiency as equal to the hot temperature minus the cold temperature over the hot temperature. Right, so that will be pretty straightforward. 480 minus 300 and then divide by 480. So 30.5% Alright, so now we have to look at how efficient it's actually being. Okay, so we know that the efficiency is going to deal with the amount of work that's being produced. So the work that we're producing is 1.2 kilojoules, right, which is 1,200 joules. Okay, and this is per kilocalorie of heat that's absorbed. So this is the heat that's being absorbed. That's the heat that's being emitted. So if we are absorbing 1 kilocalorie, okay, that would be 1,000 calories, right? And we also know that 1,000 calories we can turn into joules. Calories are related to joules by a factor of 4.18. So that's how many joules there are in 1 calorie, which means that we're absorbing 4,180 joules. Alright, so now we can look at the equation for the actual efficiency that we're getting. So the efficiency, of course, is the work divided by the heat in. And so the work that we're getting is 1,200 joules. And therefore the heat that's coming in, 4,180. And so let's go ahead and divide 1,200 divided by 4,180. And we get an efficiency of 28.7%. So this is your actual efficiency. This is the theoretical or ideal efficiency. And so there you go. That's the final answer. Hopefully that's a good introduction for you.